full sentences. All right, so now it's my pleasure to introduce Michalis. He was my PhD supervisor. He had a very interesting scientific career. He studied physics. He's originally from Cyprus. He studied physics at the University of Berlin. Then he did his PhD at ETH Zurich in Switzerland in the area of magnetism. He studied a lot of different things like complex magnetic systems, magnetotactic bacteria, and then he moved to Berkeley in California, where he did his postdoc. After that, he returned to ETH Zurich, where he was my supervisor. And apart from being my supervisor, he also became my role model as a scientist. Now he got appointed a professorship at the University of Louisiana at Lafayette in the USA. He's really he has done a lot of different research in magnetism. Today, he's going to speak about neural networks and how they can be used for data analysis. So, Michalis, the floor is yours.
Well, Leonardo, thank you very much for your kind and flattering words. And also thank you for inviting me to participate. I'm sorry that I couldn't be there with you. I was there, 3 years ago, 2019, and it was great. We had a good time. But planning of travel was a bit difficult. Anyway, I'm very happy to be here and talk to you. And also thanks, Vedrana, for organizing the Zoom and the technical aspect. So before I start, let me ask, who has taken a physics class? Raise your hands. Oh, good. You too, Leonardo, very good. Very good. All right. Who knows what magnetism is? What a magnet is? Okay, good. All right, so I just put a few slides together. I'm not gonna speak about a particular topic, more about the method of using these neural networks for data analysis. So it's going to be a more broad topic. But I will introduce some basic concepts of magnetism and then some basic concepts of neural networks. Who knows what a neural network is? Show of hands. Who has heard the term machine learning? Okay. So artificial neural networks is a type of machine learning. And even though in our science and physics is kind of a new thing, it's really not. It started in the 70s, and the computer science people have been using it, but now it has crossed borders into our science. And I wasn't, to be honest, a huge fan before because I prefer analytical models. You have a parameter, you have equations, you get some stuff, and it makes sense. But recently we did a study, and now I'm a huge fan because you can do a lot of things with this stuff. And also, it's a good thing to know that because you guys are now going to college or in college, and then you're going to be doing something else and looking for a job, right? So these tools are, let's say, up and coming. So if you have these tools in your skill set, it's a very big bonus for you, okay? And not just in science, but in many sectors. All right, let me share my screen. Oh, by the way, if you have any question at any point, please feel free to stop me and ask, okay? Otherwise, I'll just keep going. If I take too long, also just let me know. Okay.
General, do you hear me speaking now?
I can hear you.
Okay.
All right. Do you see the slides?
Yes.
Yeah.
All right. Okay, so I thought I would start with just sharing some stuff about the university where I work, where I have been for 4 years. So we are the University of Louisiana at Lafayette, and I have here some key facts. This is an old university. It has changed names a few times.
So we don't see your slides. We see the presentation as if you were gonna edit it.
Oh,
Yeah.
okay, then how do we do this?
You can just do slideshow and then present.
He had it, but I think he has multiple screens, so it was on the wrong.
I have 2 screens. You know what? I'm just going to remove this. And try that. How about now?
Now it works.
Yes.
Okay. All right. So, second. All right. So the university was founded in 1898. It has changed names a few times. As of 2021, we have about 19,000 students, has about 2,000 employees, out of which 750 professors, and there are 14 colleges and schools. And I will talk a bit about our department in a bit. First, let's see, where is Lafayette, Louisiana? So Louisiana is in the south. It's one of the smaller states, and Lafayette is where the peak is, about 2 hours away from New Orleans. And we're in the Gulf of Mexico, where we have particular weather. As you know, all the hurricanes come through here. But it's very nice, and we have a nice campus. This is the main building here. This is the main square, what they call the quad. That's behind the main building. And because the region has a very, let's say, particular nature, it's the bayou or the swamps. We have a lake on campus called the Cypress Lake, which is kind of a, it shows how the region looks like. And the Cypress Lake is inhabited by some tenants where we have alligators and turtles. And as you can see, they live peacefully with each other. And if you come to campus, Leonardo has been here, you can visit and watch the alligators and so on. They don't bite. Now, for the department, these are slides that I usually show at outreach activities. So we're the Department of Physics. We're one of the smaller departments, but we teach many students because everyone who has to take physics, be it engineering or other sciences, they have to come to us. So we have 8 research active faculty, 2 instructors, and 1 assistant. And there are some statistics from the past 5 years about publications and funding for research. We offer a bachelor's in physics with the typical classes, and we have concentration. So you can do physics, just regular pure physics, or you can combine and put in aspects of computer science or geology and geophysics, informatics, or pre-allied health. The last one is for those who want to go into medicine. I don't know who is familiar with the American education system. Show of hands. No. So in contrast to Europe, where you go and study medicine, in the US you have to study something and then go to medical school. Medical school is like a graduate school. Okay? So we also offer masters in physics and a PhD in earth and energy science. And we have the different research topics shown there. And for the master students, obviously, and the PhD students, we have either teaching assistantships or research assistantship. That means no one from our graduate students pays it. So you can do a PhD without paying tuition and you get paid a stipend. You can also get a master's in physics without paying tuition and get paid a stipend. So none of our graduate students pays anything, they get paid. Then we also have other activities. We have the Society of Physics students, for which I am the coordinator. And they're responsible for organizing various events like outreach activities or social gatherings. And we also organize Science Day, and I have a video that I will show you. They also do movie nights, telescope nights, and so on. And that's good because being a small department, it's easier to have a sense of community between the students. These are some statistics for working after a physics degree, which we usually show people. Basically, the message is that after physics, you can choose to do whatever you want. You can acquire some further specialization. You can just go and get a job in either industry or military or NASA or any other sector you want. And these are the typical tasks physicists have in this sector. Here's a list from our alumni, examples from the past 50 years, just to show, the width of the range of different things you can do after the degree. Now, going into the science of this, the title was Artificial Neural Network for Data Analysis. As Leonardo said, my field is magnetism, so the data we analyze is magnetic data. But first, let's talk about why are magnetic materials important. So I have these three circles here. You can see we have physics and material science, we have engineering, geosciences, and there's more, of course. And magnetic materials are at the intersection of many different sciences and applications, because you need magnets to convert energy, either from wind power to electricity, from gas to electricity, from nuclear energy to electricity. Anywhere you have a generator, you need a lot of magnets. You need magnets for data storage in your hard drive, in a computer, for example, or other logic devices. And also, magnets are widespread in biomedicine for either imaging or for treatment, and there's new applications being studied, and also for geological and space exploration. So there are many different fields where magnetic materials play a key role. And our job as physicists is to study the link between the properties of materials and their behavior, their magnetic behavior. And this is also kind of the overarching topic of this talk. So first, some basic facts, or not fact, basic concepts of magnetism. Who has heard of Maxwell's equations before? A show of hands. That's very good. So as you can see here, I have shaded out the equations because I don't want to emphasize on the math now. So Maxwell's equations are the four equations that describe electromagnetism. Okay. And these four equations say is that electric produce electric fields. The second equation says,
Michalis,
yeah.
we lost your video.
Oh. Can you see me now?
Yeah. Good now.
All right. So the second equation says that there are no magnetic charges. Okay. The third says that a changing magnetic field generates an electric field, and the fourth says that a changing electric field generates a magnetic, and so on. So these are the foundations of electromagnetism. But then, okay, if we have a changing electric field or a current, we have a magnetic field. But then how do we have materials that are magnetic without any currents or fields or anything? I mean, you all know, like a fridge magnet or one of those bar magnets or a compass. All those things are magnetic without electricity, right? So does anybody have an idea how come they are magnetic on their own?
How can things be magnetic on their own without a presence of current?
No? Well, the answer is that even though something is like a solid, a piece of iron, for example, that doesn't mean that the atoms in it are just fixed in position and nothing is moved. Because if you go deep into the structure and look at the atoms, things are moving very fast. And we have two sources of magnetic fields within materials. One is the motion of electrons. So assuming you all have a basic understanding of the structure of atoms, you have a nucleus at the center, which is made out of protons and neutrons, and then you have electrons circling around the nucleus. Okay, that's the classical model of the atom. So here in this simple picture, you have a nucleus and an electron going around. And this moving electron is basically like an electrical current because an electron has a charge. So then this orbital motion of the electron creates a magnetic field. Okay, that's the first contribution. But this thing alone cannot explain the fact that we have magnets, that we have ferromagnets. Only when people discovered quantum physics could we explain why we have magnets. And that's because of the second property, which is the so-called spin. To visualize this, imagine, so before we had the electron moving around the nucleus, and that is like a current and makes a field. The spin is when the electron spins around itself, and that creates an additional magnetic field. Of course, in reality, electrons don't rotate around themselves. It's what's called a wave that vibrates, and this vibration makes the field. But it's not important right now. So you have these two contributions of electric field inside a material. So even though something is a solid, from our point of view, electrons are moving very fast inside the material. And this rapid motion generates this magnetic field. And under certain circumstances, these electrons in these materials communicate with each other. They have what we call an interaction or a coupling, and then they all align parallel to each other. And that's when we have what we call ferromagnetism. Okay? And this, how many materials do you know that are ferromagnetic? Or first, let me ask, does anyone know how many elements there are in the periodic table?
Is it 3 or 4? Is it
3 that are magnetic, you mean?
I think.
Yeah. So it's only 3 or 4. It's only 3 metals that are magnetic. It's iron, cobalt, and nickel. So out of all the elements in the periodic table, okay, only 3 are magnetic. That's because things are ferromagnetic only when certain conditions are met. Okay, so it's a very, even though we use it every day in, either in technology or in everyday applications, this is a very rare phenomenon. Okay, out of all the elements, only 3 are magnetic. Now, so in these elements that are magnetic, we have these atoms next to each other, they form the structure, and then all the electrons are connected to each other, and their individual magnetic moments point in the same direction. Okay, so then each atom in the material is like a tiny magnet. If you put all these together, they make their fields add up, and then you have something that is a bulk ferromagnet. So, as I said, we have different types of magnetic materials, and we have different applications. We have high-performance permanent magnets, which are important for generators and motors, which means for energy conversion. And obviously, this is a very important sector because the energy demands are increasing very rapidly. So we need to optimize these materials to have a better energy conversion. And this is also a topic that Leonardo has worked on during his PhD. So you can talk to him about that after. We have soft ferromagnets that are used in transformers and generators as well. We have magnetic nanoparticles that are used in biomedicine, like in MRI or other types of medical imaging, or the newer development is also cancer therapy using magnetic nanoparticles. So they have many different applications, and also nanoscale patterns, which is, as I said, data storage and logic devices like hard drives and so on. Now, of course, all these different types of magnetic materials, different applications, but the physics of magnetism is the same for all of them, right? It's electrons, and what are the electrons doing? And the question we deal with is the fact that the performance of any type of magnet depends on this internal magnetic field, the fields that are made out of the electrons and the atoms, and how are the atoms put together, and so on. So our job as physicists is to develop methods to quantify those fields, to measure them, and then to be able to connect, okay, what are these atoms, how are they built in here, how is that material behave? That's the general question in material science, is what we call structure-property relation, right? All right, any questions so far? No? All right, let's move on. Now, there are different methods to measure magnetic properties. The one I want to talk about is based on magnetization dynamics. Magnetization dynamics refers to how the magnetic field of a material responds to an external magnetic field, because those two fields will interact. So you have a piece of material that's a magnet, and then if you put that in a bigger magnet, how will it respond? Right? That's the question. And this is described by the famous Landau-Lifshitz-Gilbert equation. Again, the equation here is faded out. It's not about the math at this point. But basically, the point here is that when you have a magnet which has an internal magnetic field, and you come with an external field and try to change the configuration inside the magnet, it doesn't just switch to the new direction. It does a motion called precession. And now let's switch to, let's run a simulation. Okay. Can you see the new screen?
Yeah.
All right. So this is a simulation of a small magnet. The arrows point in the direction of the magnetic field inside the material. Now, if I change the direction of the external field that I'm applying, look at how the moments or the individual vectors will rotate. They don't just go in the direction of the magnetic field. So the external field now points upwards. Okay. So the internal field eventually goes there, but it does this rotational motion called precession. If I try and change it again, it follows a similar motion. It kind of spirals into the new direction. So that means we are not just dealing with static things here. We're dealing with dynamic things. As I said, electrons, materials move very fast. They make fields, and those fields also move as a function of time. And the speed at which they move depends on the internal parameters of the system. So if I make the relaxation slower, they move slower and they take a longer time to reach that new configuration. Okay. If I make the relaxation faster, then they reach the new configuration sooner. Okay. Any question about this example? Do you want to try something else? No?
Ready?
Yes?
You know that you want to try something else. Okay. Sorry.
No? Okay, all right. Okay. Okay, we go back to the slides.
Yeah, one.
I have
Yes.
that.
Yes.
What we make the field stronger? The magnet.
The field inside the magnets.
No, external field.
Well, the external field is you would use an electromagnet. So an electromagnet is you have a coil of a wire that is spun around, and then you pass an electrical current, and that produces a magnetic field.
And if the magnitude is bigger, would it reach the new configuration sooner?
Yeah, so let me stop this so I can see you. So obviously, the bigger the magnet or the bigger the electrical current, the bigger the field you can make.
Their question is, if you make the magnet, the external magnetic field stronger, how would that affect the speed to which they come to the equation?
Okay, now I understand. Well, the stronger the external magnetic field, the faster it goes to the new configuration, right? And the smaller the field, the slower, and so on. All right. Other questions? No? All right.
Yeah, there is another
Okay.
one.
Yes.
Can this be used somehow in a sense that we can like produce like maybe a larger amount of, I don't know, energy or electricity because of this? Like how can this be used? What is this like phenomenon of reaching an equilibrium like for?
This is exactly the point of the next slide. Excellent question.
Sorry.
No, it's a great question. So this is the basic principle behind MRI, magnetic resonance imaging, right? So the technique I will show you is called ferromagnetic resonance. Resonance is a phenomenon when an external source that has a frequency kind of matches the frequency of, the internal frequency, and then you have resonance, this vibration of the magnetic field. And okay, I need to show the slide and then we can talk about that. There was another question.
So the three elements that are magnetic, is it possible to make elements that aren't usually magnetic?
Excellent question. Yes, it is. In fact, the magnets that are used in industrial applications, like in engines and satellites and generators, are not just iron or cobalt; they are alloys. Okay. So the strong magnets are you have samarium cobalt or neodymium iron boron. So there are different types of alloys. So for each particular application, there are magnets available that are, with specific performance. Let's see. Yes.
So the specific, when we have a specific element that has magnetic properties and we alloy it with an element that doesn't have magnetic properties on its own, does like the one that has magnetic properties kind of pull the other one into, being able to have magnetic properties?
Sometimes yes. So with certain elements, for example, with cobalt platinum alloys, okay? So you put cobalt atoms and platinum atoms. Cobalt atoms are magnetic and they have a large magnetic field, like the atomic field. Platinum atoms are not magnetic, but they have free electrons. So when they are close to a cobalt atom, the magnetic field of the cobalt atom polarizes the electrons in the platinum atom. So platinum then becomes magnetic by, let's say, proximity, by interaction with the cobalt. In other cases, you can have something that is not magnetic and then put another non-magnetic element in there, and then it becomes magnetic. So it all has to do with the number of electrons in each atom and the distance between atoms.
Thank you.
Other questions? I like having this interactive setting instead of me talking the whole time. Other questions? No? All right. Okay, so let's talk about ferromagnetic resonance. So we saw how the external field has this dynamics, this precession, and so on. Now imagine that you apply a field that is changing, an oscillating field, okay? So depending on the dynamics of the material, it will depend, that will decide, can the magnetic field of the material follow the external field, and so on. And this is what we do in ferromagnetic resonance. So we have two different fields. We have here this electromagnet, this is the sample here. So the electromagnet produces a steady field in this direction. And then there is a microwave here, a transmitter, that sends a microwave here. Now, the microwave has electric components and magnetic components. Here we only care about the magnetic component. And the microwave has a certain frequency in the range of gigahertz. A gigahertz is 1 billion hertz. So that means the magnetic field at the sample changes about 1 billion times per second. So then how the material behaves depends on the frequency, the type of material, and so on. And you saw how, like the question that was before, how does the speed of the magnetic field in the material depend on the strength of the external field? Okay. That's something that's called the Larmor frequency. That depends on the external field. The bigger the field, the faster it will go. So then depending on this steady field here, the material has a certain frequency that it oscillates. Now, if the frequency of the microwave is the same as the frequency because of this Larmor precession, okay, then we have resonance and the sample absorbs all the microwave radiation. Now, the second question was, how do we use this phenomenon? Why is it useful? Because this is the same principle as is used in MRI. And also, it's the first type of resonance was NMR, or nuclear magnetic resonance. So because all these things depend on the elements of the electrons and so on, this is a spectroscopy method. So by performing experiments like that, it's like you can put the sample in there and decide what it is based on how it behaves. In MRI, what you have is you have 3 different fields. You have a steady field, an oscillating field, and a field gradient. So if you put a person in the MRI, you have these 2 fields, and you have a field that changes strength along the length, and that gives you the ability to make a map based on the strength of the field. And then the water molecules in the person undergo this resonance, and this is then measured by the receiver. And because you have a map, because you know how strong the field is in each location, you can recreate a map of the inside of, of the person. That's basically, let's say, very crude, how MRI works, is resonance. Any questions about that? Obviously, I don't expect you after one slide to be experts in resonance. Here, we're just interested about the key aspects of it. All right, so we have this method, and what do we measure? So we increase the steady field while having the microwave field go in the sample. And when the strength of the field is such that the frequency becomes the same as that of the microwave, it absorbs the radiation, and we measure this absorption. Okay. This is the derivative of the absorption. That's a technical issue, but this is what the signal looks like. And it has two characteristics: the resonance field, which means at which external field do we have resonance, and the width, this delta P. The width depends on the relaxation mechanism. Remember, in the simulation, we made it faster and slower and so on. This delta P depends on that. And this depends on the internal magnetic fields. How? Let's imagine you have this needle here, and it's magnetic, like a compass needle, okay? So this needle here has its own field that is along the axis of the needle. Now, if you run this experiment of this needle with the external field parallel to the needle, because the needle already has a field in this direction, you need a smaller external field to achieve this resonance. So we go from, let's say, here to here. If you do it like this, the field of the material now is in this direction. So, but we are measuring this direction. So you need a bigger external field to compensate for that. So the signal moves to a higher field. Okay. If you have both, if you're measuring two needles, you're going to see both signals. So what's the key here? The key is that the spectrum here, which is important to measure these fields, depends on the type of magnetic particles you have in your sample, okay, and their configuration. And what we see here is that this spectrum here has information. What information? The information I have here is that my sample consists of, let's say, two needles, one that's lying like this and one that's standing like that. And again, why is that important? Well, because by quantifying these internal magnetic fields, we can improve methods like, for example, MRI, where we use magnetic nanoparticles as contrast agents. Okay, let's say you want to image a brain or some part of the body. You put magnetic nanoparticles and they give you a contrast from their resonance. So it's important to know precisely these things if we can apply them for any other type of application. And now from a real experiment, this was from a recent article we published last year, where we took this is a microscopy image, okay? These shadows are magnetic nanoparticles. Okay, the size of these things is about 50 nanometers. Do we all know what a nanometer is?
Yeah.
Yes? Okay. So 50 nanometers means is about like 1,000 times smaller than, the average human hair. And this is the size of nanoparticles that is typically used in biomedical applications. So this is an important type of material. So we put this in our spectrometer, we made experiments, and you see that we get these signals, all right, which they're asymmetric. So if I go back, this is a nice symmetric signal like this, okay? It's a simple signal. Here, this is wider here, not as wide here. There is some kinks here. It's broader here. So it's asymmetric, it has inhomogeneity. That means this spectrum contains information, okay? Why? Because like with the example here where we had two objects and they do what we call superposition. So their signals are superimposed. So you have both signals in the spectrum. It's the same as here, but here we don't have two. We have millions of particles that are maybe turned to a different direction or have different shapes and so on. So this superposition gives us this. And this spectrum here is as we measured it when we received the sample, which was in some liquid form. So the particles were in a liquid, what we call a suspension. This here was after we dried it. So what changed here is only how the particles were turned, okay, inside the sample. So you can see a change in the behavior. Now, I write here that these things have information, okay? The question now is, how do we extract this information? Now you see these dashed lines here, these are calculations, but what's the problem? The problem is that if we know the material parameters are the internal fields, depending on the elements you have in the structure, the size of the particle and so on. If we have the material parameters, we can put them in our analytical model and compute an FMR spectrum. But there's no inverse way. So we can't take an FMR spectrum and put it in a model and get the material parameters. So the way we fit this is by trial and error. We say, okay, let's say it has this much field in it and it's like that. Let's calculate it and compare to the experiment. Does it look good? No? Okay, change this. So it's like that. But it would be beneficial to have an inverse method here, where we can take an FMR spectrum and just by looking at the spectrum, knowing what type of fields we have in the sample. Okay. So this is the challenge we have here in our research. And not just that, this is, the whole field. There are no inverse methods for this, for most magnetic methods. And this brings us to the main topic, which is the use of artificial neural networks for identifying this. And this is, I have here, this is a preprint for anyone who is interested. We just put this up this summer. And this was the first time for us using this. And it's kind of an exciting topic because it has a lot of potential. So if you're interested, you can go on this address and download it, it's free, or you can email me and we can discuss. So what's the idea here? The idea is to, since we don't have a model to go from spectrum to material parameters, is to take these artificial neural networks, train them to know this spectrum, and then if we give them enough data, then we'll be able to show them a spectrum and the network will tell us the material parameters. Okay. So here I offer, this from our paper, a very general description of what is an artificial neural network. A neural network is basically something that mimics the brain, where you have neurons, which are, say, centers, which are connected to other neurons. The basic principle is you have, in artificial neural network, you have layers of processing. You have the input layer, which is the data you provide, and the output layer, which is what you get out after all these numbers have been crunched. And you have what's called hidden layers. Okay? And at the end, we will make our own network and do live calculations. But basically, the gist is you have neurons which are connected to other neurons, and these connections have weights, right? But I don't want to have it so that, vague. So we will do an exercise, right? So for our study, we used two different architectures of neural networks. The one was the so-called convolutional neural network, and the other one was the multi-layer perceptron. Now, these have, you can use these, so we use the platform called TensorFlow. So TensorFlow is a library for machine learning methods, and if you know a bit of Python, you can go to TensorFlow online and use these neural networks free of charge. You can use basically Google's computers. Because TensorFlow is a product of Google and it's free, and you can use their computers to do this calculation. Who knows how to program with Python? All right. So I don't, okay, but I'm given to understand that it's easy to learn if you know a bit of programming. So my graduate student who did this is not a computer expert. Okay, he's older than me and he had difficulties finding the button to turn on the computer. But now he's doing neural networks and machine learning and so on. So it's very accessible. So you can go and practice and so on. So let's talk about the multi-layer perceptron. What is this with the fancy name? So you have the input layer. This is what we use in our study, the input layer and the output. Our input layer is the fMR spectrum. If I go back, the information is X, let's say 100 and the value here. X, Y values, it's a table, okay? That is the values of the spectrum. So we feed those into the network. And each dot here represents a neuron. Now, these numbers are propagated to a next neuron, and all these connections here are weights. So basically, you are doing a number crunch where you combine all these numbers and go from 7,000 values of the input down to 2. And the idea is that you have a spectrum coming in here, and the material parameters are supposed to come out here. And the way this was done is by what's called supervised learning. Okay, we'll see how that works. The other one is the convolutional neural network. So instead of here, you can see that each neuron is connected to each other neuron of the next layer. You see, this, for example, connects to this one, all the way here. And then this one connects to every other neuron here, and so on. So that's why they call them dense layers, because they're connected to all other neurons. A convolutional neural network is different. It uses convolution, where you have the input. This convolution here is basically reducing the number of data. Okay. How does that work? You have a filters, let's say filter 1, 2, 3. This is an example data. You have the input data, and filter 1, let's now is filter 2, is applied here. Basically, you multiply this number with the first number, the second number with this number, so on, and then you add them up. And that becomes the result in what's called the feature map. So the characteristic things here, you have the filter or the window size. Here's 4 data points, okay? And then you move along your data with a stride. Here the stride was, the stride here is 2, because it moves by 2 data points each time. And then you see the calculations here, and then it makes a reduced data set. Now, I have an exercise for you, but let's see if we have any questions so far.
I have a question. How do you choose the filters for this evolution?
I couldn't hear you very well.
How do you choose the filters, the numbers in the filters for this convolution?
Okay, so this is a good question. The answer is there is no answer. Okay, so for each use, you're going to have a different architecture of the network might be required. So for each purpose, you need a different architecture. And we will see at the end how that works, right? But yeah, it's a great question, because when my grad students started working with this, I also asked the same things, like how do you choose the window or the stride or the filters and so on? And he was like, whatever works. Okay. So, but first, let's try to understand how this convolution works. All right. So does everyone have like a piece of paper and a pen or a pencil? By the way, am I taking too much time?
No, just go ahead.
It's fine.
It's with the paper.
Yeah.
Okay. Now,
So just feel free to take time.
you see how the convolution works here. Now we're going to do, see, for artificial intelligence, we don't always need the big computers. We can do with pen and paper just to understand the math behind it. So this is the exercise. You have this data set. You have this filter.
Can you just wait for a bit longer so that we give everyone a paper? Does anyone else need a paper?
Okay. So let's do this. Everybody, please write the numbers here for the data and for the filter. And I'm going to go to the previous slide and have the animation run so that you can see how it works. All right?
Yes.
Everyone has the numbers?
Yeah.
All right. Okay, I'm going back to this slide and let's take 5 minutes. All right? Now this has 3 filters. In your exercise, there's only one.
One.
What is our window size in the task?
Excuse me?
The window size in the task.
Here, 2.
Oh,
2 data points. So I'm going to show the first step.
Wait, there is a question before.
What if the window size, what if we have an input that's not divisible by 2, but the window size is 2? Then how does it move?
Well, that's so you will have to adjust it so that you have, if it's not divisible by 2, you have a stride that gives you a complete, let's say, rotation of the data.
So we get the input and then we make up the stride.
No, here the stride is given. You have a filter with size of 2 and a stride of 2. So that means you start, let's say, from the left. It's 1 times 1 plus 1 times 2, that's 3. That's your first data entry here. The second, we move the filter by the stride, which we said is 2. So,
Has anyone solved it?
Yeah.
Maybe we can just check with them what the answer is. Maybe they,
okay. Well, the answer would be 5 numbers here. So the second step is this, and this, and so it's 3, 4, 4, 4, 5. Who has the right answer? Right. Who does not have the right answer? Don't be shy, it's okay. Everybody has the right answer, great. You guys are smarter than me. Okay, okay. Now, there was a question? Okay, now we can continue the convolution by using, that goes back to your question, what if it's not divisible, the size? Well, now we have 5 data points is the result from this operation. The window has a size of 3, so 5 is not divisible by 3. But we use a stride of 1. So I want you now to do the same procedure with this data as input and this filter. Who needs some more time? Everyone is finished? Yes.
7, 8, 9.
7, 8, 9. Is that what you got?
Yes.
Yeah, that's what they said. You maybe didn't hear them.
I heard the 7 and 8. Okay, excellent. And now we can apply this filter again, and we get the number 15. Okay. So, okay, what have we achieved? Well, we went from 10 numbers to 1. This is what a convolution is. Okay, we have convoluted this data into a single number. But then how can we go back? How can we associate this with that? Well, this is done through these filters. Okay, so the information in this convolution network is in these filters. So in the same way, we can go from a spectrum, which is a table with X and Y. Now we had a single column or line. Here it's just 2 columns, right? We go from this, which is, let's say, 7,000 data points, and apply this convolution down to 2 numbers. And the training, the supervised learning, is done how? We give the spectra to the network and we label them. What does that mean? That means you tell the network, take the spectrum, and at the end of your processing, your 2 numbers should be these 2 material parameters. So then the network applies these filters, what we also call weights, and then it adjusts these weights so that the numbers at the end are what you want. Okay, so the training is this weight adjustment. And here we're comparing the input values, the material parameters, with the output after the network has been trained. So it has an excellent agreement, so the training works very well. And let's say the success of the training is measured by the loss function. Loss is how much basically the predicted values by the network agree with the target values during the training. And of course, your goal is to minimize, so to go to 0. And then we tested this. I'm not going to spend much time on this because we're already like an hour into this. And then we tested this. So we tested this with FMR spectra that were unseen by the network. So before we gave the networks FMR spectra and we had them labeled, saying these are the material parameters associated with this data. After the training, the weights are fixed. Then we gave the network just data without telling it what the material parameters should be. And you see here the Black is the input, like the test data, and red is the output, the prediction. And look at the excellent agreement between prediction and target. And most importantly, these gray areas here correspond to material parameters that are beyond the range of the training data. So that means that there is a possibility to extrapolate. So not only unseen data within the range of the physical parameters, but also slightly beyond that range. So this is a very encouraging result, because that means we can indeed use this for our purpose, which is if we can train an artificial neural network with enough data, then we'll be able to show it data and it will tell us what fields are in the material. And here we're comparing material parameters. We'll compare spectra with those material parameters. This here is the worst prediction, and it's actually not that bad. So what we find here is that if we train these artificial neural networks with adequate data, then we can make predictions about the material parameters very accurate. And this is basically the main finding of this study that I wanted to show you. Do we have any questions so far? We're very close to the end now. Do you have any questions? No? All right, no. Yes?
So, how do you reconcile this this kind of linear algebra game with causality connections, which you usually get predictions in physics?
I'm sorry, there's a lot of echo, and I couldn't make out the question. I'm sorry.
How do you reconcile this kind of linear algebra game with the usual method with which we get predictions in physics? I mean, using causal relations and deriving formulas from known laws.
Well, so the question is, let's say, numerics versus analytics, if I understand.
Yes and no, in that sense. I know it's a huge topic, but yeah, what would be your opinion on that?
So, if I understand your question correctly, is what do we understand in terms of physics from these linear algebra operations about these neural networks? Well, the answer is no physics, right? So this is really just numerical brute force calculations. The neural network doesn't need to know what the physics are. It knows what to expect based on the number it has, okay? And this is done with supervised learning. Now, there is an additional level of what's called physics-informed supervised learning, where it's not just giving data to the network, it's giving data and building in the forward model, the model where you go from parameter to data. So you build the model in there for the train, but then when you test the network, it's just the linear algebra in the network. Does that answer your question?
Well, okay, for now, yes. Thank you.
Okay, so that's why I said in the beginning that I wasn't a huge fan of these techniques, because there's no physics, right? So what do we do in physics? Physics is we make an observation, like, oh, there was a lightning outside. And then we make an assumption. Let's say, okay, let's assume that there was a charge buildup, and that led to this big potential that made the discharge, what we saw the light. And then we put the calculations down, and if the prediction of our assumption is similar to what we observed, that means our assumption is valid, right? This is the general premise of analytical modeling. You make an assumption, you use that to predict a certain behavior, and if the behavior you predict based on your assumption is close to what you observe, you have a valid theory or a valid model. With these artificial neural networks, it's nothing. It's just numerics. Okay. And there was a question before about how you choose the window size and so on. Again, there's no answer. Whatever works each time. Okay. But that's why, I mean, this sort of techniques are not going to replace theoretical physics, right? Because like the topics I showed you are more in the realm of applied physics. So this is more of engineering. So we already know the physics of FMR and these particles and the magnetic fields, but we need applications so that we can use them in other situations. So this is more in the applied spectrum. Some people have used it to get new physics. Now, I don't know details about that, so I'm not going to be, for or against, I don't know. But you can use this to train. Let's say you have an equation that is not solvable. Okay? Like, for example, Schrödinger's equation in quantum mechanics. Like you can solve it for 2 electrons, okay? But you can't solve it for more than that. So if you can train a neural network how to solve it, then that will be, let's say, a new field. That's what I can imagine that can be done. But in our lab is more on the applied side, how can we use this to solve our problem? Other questions? Okay, now let's, yes.
I have a question. I might have missed it during the talk, so sorry if I'm actually asking something you mentioned, but for me, it's not clear how was the initial training done? Was it just a lot of spectra that were fed to the neural network?
Exactly. So, as I said, we have a model where if we can put in material parameters and then we can calculate the spectrum, right? That's what we call the forward modeling. We go from parameters to spectrum. So, we used a range of material parameters, and with those parameters, we calculated a bunch of FMR spectra, like 1,200 spectra. Then when we put in the spectra in the network, they were labeled. Meaning what? Each spectrum is associated with these material parameters. So the network starts with this input and crunches all the numbers and adjusts the weights so that the 2 numbers at the end are close to the material parameter.
So all of the spectra that you fed the neural network with were theoretically produced spectra for given material parameters.
Yes, they were all computed spectra.
So how can you know that you haven't just created a software database of your spectra and you're just getting like the theoretical predictions back to what you started with?
Well, because that was the point with the data that were beyond the training range.
Okay,
so of course, with these sort of things, it is possible to, I mean, we say also in the paper that we can extrapolate, but in reality, you should. Okay, it's risky, let's say, because you can also overfit certain things, and So as I said, this is like a new kind of thing, so we're still experimenting.
Okay, thanks.
Yes.
Yeah.
So I may have also missed this in your presentation. So this mechanism was based on theoretical spectra, and then those 2 anisotropy and the line with essentially the last 2 points. But can we go from experimental data where we know those 2 points, and then for some where we can empirically measure the spectrum and then compare experiment with theory, or only theory and then what we get from the computation? So maybe it's a little confusing. I'm asking if it is possible to compare computation with experiment and not just the theory with the computation.
That is a great question. The answer is yes. The reason we used theoretical data is because, sorry. So with our model, we can calculate FMR spectra with a large window of material parameters at fixed lengths, fixed steps and so on. with experiments, you can't just order particles that have this and this and this. You know, you can have 4 or 5 different kind of stuff, and then things that are in between. But the point that the reason we want to develop this is that because if you measure something experimentally without a model, there is no way to interpret. But by training the networks with known data, and we have a comparison between theory and experiment, so let's say we have fixed points of comparison, if that makes any sense. So the answer is yes. Right? Other questions? All right. Now, before we finish, let's go do some neural network stuff. Not with magnetic data now, but just I want to show you that you can go and experiment yourselves. So this is the website of TensorFlow, which is the library I told you that has been developed by Google. If you Google TensorFlow, you can find this. So here you have the structure of the neural network, and you can change this. And you can do either regression or classification. Okay, let's start with classification. And we can choose different data. Let's choose this. So the dots here are data points, and the background is the prediction of the neural network. And I have this architecture here. Now, I can control the learning rate, the activation function, and so on. If I run it, I see that the network quickly, after 100 epochs, realizes that, yeah, this data belong to this class, orange, and this data to this class, blue. Okay. Now, if I take something a bit more complicated, like this, let's run it again. So this doesn't work as fast as the other one. Why? Because it's a more complex structure, right? Now, there are different things I can do here to improve this. So these are the inputs I'm using, okay? So basically, the result of this are linear combination of these two things. But if I increase the possibilities, okay, and run it again, now it's looking more like what it should be. Okay, but still it's not getting close. Any suggestions as to what I can do? So again, we go from input to output, and the whole process depends on the hidden layers, the number of neurons and so on. So what happens if I increase the number of layers and the number of neurons? It's trying to do something, but it's not really getting there. What happens if I change the activation function? Obviously, the other one was better than this. So this goes to the question, how do we decide the architecture of the network? There's no one answer to that. It depends on the data. Like for this simple system, one hidden layer with 4 neurons was enough. Okay. Now it finds this prediction, and we have a loss of 0.14. If we change the activation function to the hyperbolic tangent, we have a much better result. The loss function is much lower. So it depends on both the activation function and the architecture. Yes.
How do you explain that it works better for more complex structures?
I do not. So that's the whole point here, because this is a very complex kind of numerical system. So it's not, it depends on the case each time, on the structure of the data and so on. Let's try to do regression, for example.
But wouldn't it make sense that for a more complex structure, there is a more unique solution? So then-
Exactly. So the more complex the structure, the more we can test it here, right? So we have this input here, these properties, and we have in the hidden layer 2 neurons. Okay, and let's run this for 100 epochs and see how close we get. It's not really there, and the loss is 0.03. Now, this is kind of a complex thing. It goes from blue to orange, blue, and then orange, blue, orange, right? So it has a certain complexity. So what do you think I should do to increase the performance of the network? I can change the activation function. I can add more layers. I can add neurons here. What do you think? Take a guess.
Add neurons.
Let's add neurons. Now, so we had 0.03. After 100 epochs, it's about half the loss, so it's closer. If we add another layer, after 100 epochs, it's slightly better. So by adding neurons, I gained something. By adding layers, it didn't change much. So let's increase the number of neurons. Okay. It's getting closer. How about the activation function? It doesn't have as good of a result. So let's go back to tangent hyperbolic. So I can increase the neurons here as well. I can increase the neurons here. And I see that by increasing the neurons, I'm getting much closer to the target value here. Right? So if I keep increasing the neurons, I will get much closer. I can include these things too. And why is that? Because the information, the training of the network lies on the weights. The weights are these lines that connect the neurons. Now, so I showed you 2 neural networks before, a convolution neural network and a multi-layer perceptron. Can anyone tell me what type of network this is? By looking at this? Do you see convolution or do you see this MLP thing? No. Nobody wants to answer. It's getting late. So we see here that each neuron is connected to each other neuron in the next layer, which is similar to, let's go back to the slides. It's similar to the multi-layer perceptron, which historically, this was the first implementation of a neural network back in 1967. Okay, this came in later. So by doing the simulations, I just wanted to show you that you can, there's a website, there's not just one, there's more. You can go there and play around and try to understand how these things work, right? But I will finish here and conclude with this. Like you're going to remember anything from this is that magnetic nanoparticles are important structures for a wide range of applications, from energy conversion to biomedicine, data storage, a lot of important sectors. Our work is to connect properties and performance, okay? And so we need methods. One of the powerful methods is ferromagnetic resonance spectroscopy, which is the method we talked about, which is, as I said, similar to nuclear magnetic resonance, what is used in MRI and so on. And our problem there is that we do not have inverse methods. We can't go from spectrum to parameters analytically. But we have this study here that we can say it's kind of promising to use this machine learning techniques, these artificial neural networks, and if we train them enough, they can recognize a magnetic material from its behavior. And there is a lot of room to explore yet the applications of these sort of things. And especially for you who are now starting either college or grad school or whatever, that these newer techniques are good things to explore, because if you go and look at ads for positions now, okay, you're going to find this machine learning component in many ads for positions. In fact, even in the tech business in San Jose and San Francisco, the best positions now are those that deal with machine learning and artificial neural networks. Because these are, I mean, for our field, the application I showed you is a very, very rudimentary application of this. There are way more advanced applications of these machine learning things for software and computers and so on. And with that, I want to thank you for listening. Thank you for engaging with your questions. And it was a pleasure talking to you. And if you have any other questions, I'll be happy to answer.